Okay, so thank you very much. So my name is Tatsuhiro Naka from Toho University. So thank you for inviting me. So such very interesting workshop. So I'd like to talk about the Paleo Detector. So and actually, so my background is experimental particle physics. So and I don't have the expertise of the geoscience. So and so in here, so I'd like to discuss about the particle physics, so using the and collaborating with geoscience. So and now, sorry. Okay, so now and we are the collaborating. So with the people in Japan. So and this is Japanese collaboration, the cooperation. So and so such as the Jamstacks and Nagoya University, Kanagawa, yeah, and so on. So and in here, so and there are the various the people. So with the various background. So such as the particle physics and astrophysics. So geoscience and material science and so on. So it's very interesting collaboration. So and my major is particle physics. So and for example, so detectors are part. Yeah. So in here, so I focus on the paleo detector. So and in the particle physics, and the detector is very important. So and for example, so this is the example of the detector for the particle physics. So and for example, the scintillator, so and such as Cameron and also Cherenkov of detectors. So that, yeah, for example, yeah, so the famous detector is the super Kamiokande. So and I'm expert of the tracking detector. So and especially I study about the nuclear immersion. So and this is a very high resolution tracking detector. So and yeah. So and semiconductor and so on. So and such a detector is very important to discover for example, the new particles and the phenomena of the particle physics. So and this unique detector is very has the benefit to discover the new physics. So and in this talk, so and yeah, so I like to talk about the paleo detector. So and this is the new technique for us. So and paleo detector mean damage tracking detection in mineral. So and so detection principle is first. So and if the charged particles and pass through the mineral, so and then by especially the high occur the high ionization and by the high charge particle or the heavy mass or the low velocity. So and then in the local scales and occur the high dense ionization. So by that, so and here the generate the crystal defect. So and this crystal defect, so the recorded for a long time. So and maybe more than 1 giga year more. So and so however, this defect is very small. So and but by chemical etching process, so and this damage expanded. So and finally, then you can find like this the track. So and this is a okay. So and this is the fission track. So in the zircon. So and optical microscope image. So and you can find a very clear track like this. So and so fission track. So I mean this is the due to the spontaneous fission of the uranium-238. So and sometimes the uranium-238 and decay to divided the two heavy atom. So and this decay the two atoms and recorded as a track. So and so actually we know the lifetime or decay constant of the uranium-238. And this density can be measured by for example, the mass spectrometer. So and by the measurement of the fission track density, and we can obtain the date of the mineral. So and this method is a fission track dating. So and it's very popular the technique for the geoscience. So and paleo detector is based on this technology. So and so here, here, so I'd like to discuss about the collaboration between the particle physics and such the Paleo Detector the technique. So, and for the particle physics, and actually now, there are the serious problems. And this is a very important topic for the particle physics. And now, various experiments and theorists, and try to study such problem, to resolve this problem. And for example, the breaking and neutrino mass and spirogenesis and so on. And all topic is a Nobel Prize worthy theme. And here, I'd like to focus on the dark matter. In the dark matter, here I show the current our understanding of in this universe. And now, and we understand that in this universe, and the standard matter, we know yet. We know, already know there is only consists of only the 5%. And the 95% is unknown matter and or energy. And actually, we don't know only we know only the 5% in the universe, and the 95%, it's I'm not understand yet. And the case of the dark matter, actually, there are various evidence of the existence of the dark matter. And from for example, the motion of the galaxy or gravitational lens and the cosmic microwave background and so on. And through the gravity, and we know the existence of the dark matter. However, we don't know what the dark matter is. And this is the list of the elemental particles. And actually now, this is the old particles we know. And when you consider about the dark matter, actually, there is no the candidate in the standard model particle. And now we believe the dark matter should be new particles. We don't know yet. And this means very important. And if dark matter is new particles, and then here in there, something the new mechanism or new physics is hidden there. And it's very important for nature science. And the dark matter exists around us. And this is the understand by the rotation velocity curve of the Milky Way galaxy. And this is the velocity curve, the observation data. And this horizontal axis is the radius, from the galactic center. The vertical axis is the rotation velocity, of the Milky Way galaxy. And by the Newtonian mechanics, and we can calculate, calculate the rotation velocity like this. And then the visible matter, almost visible matter, condensed in the center of the galaxy. And then we expect rotation velocity curve is a degrees. Depending on the radius, from the center of the galaxy, but the actual data is the flat like this. And this means in here, in this gap, is the made by the something the missing mass. We call the dark matter. And from this observation, and we can estimate the local dark matter density. Local dark matter density means the dark matter density around us. And this value is about 0.4 GeV per cubic meter. And this mean that this corresponded to the, for example, that if you assume the dark matter mass is about 10 GeV, this means the atomic mass. If you assume the atomic mass of dark matter, and then we expect the dark matter flux, dark matter coming from the around here, about the 1 million per square centimeter per second. And now, in such, very huge, many dark matter pass through our body. Now, and then dark matter distributes around us, with very high density. But So, and we don't know what the dark matter is. So, and theoretically, so there are many dark matter candidates for the particle physics. And for example, the weakly interacting massive particles, we call the WIMP. And for example, the cuboid, monopole axion, and so on. So, and there are many theoretical candidate predictions. So, and in the Paleo detector, so and now so I focus on the WIMP and the cuboid, so in here. So, and actually, so and there are a previous study by the Micah, so in the around the 1919. So, and I will show later. So, and this first, and WIMP dark matter, WIMP, so is the most popular the candidate of the dark matter. So, and almost people so believe the dark matter the exists so as the WIMP condition. So, and WIMP so is this is a very simple name. So, and so WIMP is so WIMP dark matter should have the first so and massive particles. So, and mass so should be more than the atomic mass so or more, and so interaction so should be very weak, so such as a neutrino. Okay, so and the WIMP, so case of the WIMP dark matter. So, and here's and the detection principle. I show the detection principle of the WIMP dark matter. So, and detection principle is very simple. So, and so because we so expect the interaction and scattering so between the dark matter and the target nuclei in the detector, so such as the billiard. So, and also the dark matter velocity so is a very low speed. So, and for example, the usual the particle physics, and we use the very high speed particles, so and almost the same speed of the rate of speed, but several hundred kilometers per second. So this speed is very low. So, and actually, so this is the difficulties to detect the dark matter. So, and because if such a low velocity particle, so the interact so with the target nuclei. So, and this nuclear recoil signals is about the 10 or 100 keV. So, in keV scale is very hard to detect. Yeah, to detect the such particles, especially then. So, we have to distinguish the signal from the background. So, this is the difficulties so of the dark matter detection. So, and also, and this so track range, so recoil range is about the nanometer scale. So, and yeah, actually, yeah, so dark matter detection so is the very challenging, challenging. So, and now, so and there are the many so experiments so in the world so to try to detect the dark matter so using the such so the concept. So, and first, so the expected number of the number of signal, so is the proportion to the event rate, and finally, so depending on the mass scale and the time scale of the exposure, the observation. So, and so this event rate, so this event rate is depending on, for example, the target nuclei and the flux of the dark matter and the cross section. So, and this cross section is this is the corresponding to the character of the dark matter itself. So, and finally, so and we want to understand this cross section. So to understand the dark matter itself. So, and to improve the sensitivity to the dark matter, so important point so is the mass scale and increase the mass scale and the time scale. So, and so this picture is a current biggest experiment, so direct to dark matter search experiment, and this is the Xenon experiment. So, and now, so this experiment is running in underground, so deep underground, so in the at Italy, the Grand Sasso Laboratory at Italy. So, and this, so for example, this experiment so has a target mass is about a 10-ton so scale experiment. So, and actually, so this experiment so is the actual detector, so and exposure time scale, so it's about several years like this. So, however, if you so if we assume the paleo detector, so in the mineral, then if the dark matter so recorded in the mineral, so and the time scale is expected to be the 1 gigayear scale. So and then so exposure is larger than current biggest experiment, even though the mass scale of the 1 gram scale. So and there is a very good advantage so for the paleo detector. And also the paleo detector so is a passive detector. So it's very interesting point. So and because so actually now so in the various theorists and cosmologists so is simulating the dark matter distribution around the galaxy. So and so we expect the dark matter density so is not uniform around in the galaxy. So and so distribute the various sub-halo. So and solar systems again. So and the solar system is running in the dark matter halo. So with the density so fluctuation. So then the mineral so and may so record the such information so during the 1 gigayear scale. So and because the revolution period of the solar system has a 0.2 gigayear. So and already done the 5 cycle so in the galaxy. So and if so in the mineral so record such a dark matter and if so recorded such a density the fluctuations or the information so recorded in the minerals, and it's very interesting for the galactic archaeology. Okay, so and the previous research of so actually so there is the previous research for WIMP search. So and this is a pioneer. So and this so the experiment so have done around the 1990. So using the Moscovite mica. So and by the Daniel Snowden and so on. So and okay, I don't explain in detail. So but they measure the HPIT. So by the readout of the AFM. So and try to so distinguish the signal of the dark matter. So and distinguish from the background. So and so so they got like this the upper limit of the WIMP dark matter. So using the mineral. So this is the first time the experiment using the mineral. So and this is a pioneer. Then actually this sensitivity is not so high. So but it's very interesting. So research of the pioneering so experiment. So and this is 1919. So and recently, so and Sebastian Baum and other people so try to estimate the sensitivity for using the paleo detector. So again, so and if so actually this is 1990, but so if we can use the cutting edge technology, so and this the experiment, so and the technique, so will be improved. So and then so and the paleo detector so should be the work so as very interesting so dark matter detector. So and there estimating the various background effects. So and the effect depending on the dark matter mass and so on. So then so and as conclusion of the plot. So and first so and the dark matter sensitivity so of the paleo detector is corresponding to the okay so and all consistent the sensitivity. So with the current highest sensitivity experiment. So with a 100 gram scale and 1 gigayear sample. So if so such the detector, so paleo detector, so read out the 100 grams. So and if so this paleo detector so has a 1 gigayear scale, so the exposure time. So then so this sensitivity so will be same achieve the same level. So with the current the best limit of the dark matter. Sorry. So and maybe it's difficult to see. Yeah. So and however so and so there are many subjects so to achieve that. So and for example, so in this so plot is the assume the for example uranium chain the background is about the 0.01 ppb. So, and this means we need the low uranium contamination and also the low neutron level, so neutron background, because the neutron so make the same signal of the nuclear vehicle. So by neutron, so and this is almost the same signal so with dark matter. So and the neutron so will be background. So and such a we have to consider such a background, and also and we have to understand how much the track formation efficiency on the, for example, the LIDAR technology has to be developed. Yeah, this is also the subject of the Paleo Detector. So and recently now, so and I'm interested in the Q-ball dark matter. So and this Q-ball so is the candidate, one of the candidate of the dark matter. So and this is a actually so mechanism is very difficult. So for and well, this is the current one of the kind of the quantum condition. So with the new particles. So and like this the new quantum the condition so generated in the early universe. So and this so Q ball, so regular ball. So and this Q ball so has the so we expect that Q ball so has the electric charge. So and also the mass, so Q ball mass so should be very so heavier so than the standard WIMP so dark matter. So and the mass so is expected to be more than 10 to 10th GeV. So and the mass is very long, heavy, and it should be charged. So and this means it's so easier to detect the more than WIMP dark matter. And so Q-ball so is very so interesting point. So is a Q-ball the model so can be resolved the various serious so problem for the particle physics. For example, the hierarchy problem of the energy scale and the baryogenesis. Baryogenesis means that this is the mechanism of the baryon, the generation of the baryon in the early universe. So and the dark matter. So and the Q-ball so can be resolved such the problem for the particle physics so simultaneously. So and it's very important point. And the current so and the Q-ball search so already done by the, for example, the macro experiment. So and this is this experiment so carried out in the period of the 1990 to 2000 like this. So and the macro experiment is distributed the plastic plate so the damage so detector so and called the CR39 so distributed a large area so such about the 10 times 10 square meter. So and the exposure time is several years. So and this so experiment so try to search the Q-ball. So and here, so this line. So and this is the Q-ball so the upper limit of the flux. So depending on the Q-ball mass. So and the macro is here. So and the upper here is excluded by the macro. So however, and here there is a higher sensitivity so line. So and this is a mica. So and this is so actually so and the mica in the mica so and sorry so but the 19 so in the same era so around the 1919 so and Price and Salmon so and to try to search the monopole by the monopole by the mica. So and the monopole and the Q-ball is almost the same signal so in the mineral. So then this line is converted to the monopole search, so to the Q-ball search. So and the mica so is the analyzed area is just the 10 by 10 square centimeter. So but the exposure time so is a 1 giga year. So and this very small the mica is the sensitivity was higher than such a big experiment. So it's very interesting. So and so expected signature so of the dark matter. So and then so WIMP and the neutrino case in the nuclear vehicle is the track length is very short. So and so actually so there are some challenging points. So however the Q-ball case in this Q-ball is very heavier so dark matter. So and pass through the materials. So and then so we expect to see the likely it's a long track so in the penetrating the mineral. So, and it's easier to distinguish the signals. And so we expect there is no background for that. So, and it's easier. So, and now, and I'm interested in this, so the keyboard search. So, and now, so and we start to develop the new techniques to search the keyboard. Okay, so and so actually the subject from the experiment side, so for the Paleo detector, so and in our side, this means the particle physics side. So and we have to understand the torque formation efficiency and the handling, so optimization, so such as for example chemical etching, so and so on. So and also the readout technology is very important. So how so we can read out the signals in the mineral, and also geoscience side. So and actually I don't have the expertise, so and but it's better to use the older samples and also the low background samples, such as the very low contamination of the uranium and other radioactive background. So yeah. Okay, so and when we consider about the formation, track formation, so in the mineral, then we have to understand the mechanism of the track formation. So depending on the energy deposition by the particles. So, and this is the energy deposition so image, so depending on the velocity. So and the usual, so and the red, so is the electronic stopping power. So this is the collision by the electrons. So and then the energy loss by the electron collision. So and then blue is the nuclear stopping power. So and this means the collision by the atom. So and usually high energy physics. So and we consider only the here. So and around here the electron stopping power. So this means the ionization is dominated. So however, so in the case of the dark matter, so the velocity is very low, so in several hundred kilometers per second, and we have to consider around here. So in this region with the energy loss mechanism is both the nuclear stopping power and electron stopping power. And actually energy loss process is so different from the high energy physics, high energy particle. And in past, so and the track formation efficiency, so the investigated using the ion beam. So and so this is the very old paper, so in the 1966. So and here, so in the horizontal axis the velocity and the vertical axis the energy loss. So and this black point, so this is the case of the complete track formation. And so broken the circles. So and this is no track. Okay. So and if you see that, so and you can see here is the obtaining the track. So and this is so from this result, so and you can find the threshold of the energy loss about more than 10 mega electron volt per milligram per square meter. Then maybe so and from that, so and the threshold should be here. So and this region is the ionization so dominated point. So but then you can find here. So and this here and the track formed even though the less than this threshold. So and because so maybe so and here in the low velocity region, so in the low velocity region, so in the track formation so should be enhanced. So and actually it's not clear, but maybe so in the nuclear collision so is enhanced to form the track. Okay, so and recently, so and Hirose-san, so and of the Jamstack, so and tried to check the track formation efficiency by the ion implantation system. So expose the low velocity ion, so and expect to the dark matter signals. So and he tried to check the AFM. So and he observed the very clear the H-bit like this. So and so actually, so lighter atoms, so, such as the oxygen, so maybe the track formation is low, but the heavier the atom, so and so can be formed the track in so this is the mica. So and this is very so interesting study. So and yeah, so and such a nuclear vehicle, so can be the form the track so in the mica. So and but so difficult point, so is, for example, the AFM, the scanning speed is very low. So, and we have to read out the gram scale 100 gram more. So, and then AFM is impossible so to read out that. So, and we have to use the high speed scanning, so as first trigger. So, and then the optical microscope, so is very important. So, and then now, so I'm using the nuclear immersion. So, and in the case of the nuclear immersion, so we are using the automatic optical microscope system. So right there. So, and this is the okay. So, and this is the automatic optical microscope system. So for the nuclear immersion, so and here, then we can get like this track. Correct? Yeah. So and right by using that, so and we can scan the mineral, so the high speed and the high volume scanning is possible. So and then so this system so will be applicable so in the Paleo Detector. Okay, so and okay, so and recently and we checked the QBO the detection performance so using the ion beam. So and using the HIMAC. So and this is the accelerator for the heavier ion therapy. So and yeah, so and by using that, so and we expose the ion the beam. So and control the velocity so by the attenuation. So and we control the velocity. So and we checked the detection formation. So the expected the QBO energy deposition around here. So and so this is a result. So and we can get here. So and if we observe the microscopes, and you can see the very clear track like this. So this is the ion beam track right there. So and this white dot is the alpha recoil track. So due to uranium 238. So and maybe so and this white spot so will be background for the WIMP site. So but the case of the QBO, so and QBO track is should be the very longer track. So like this. So and it's very clear. So identification is very clear, so and it should be no background. Okay, so and now so and we are evaluating the track formation and the contrast of the microscope and so on. So and the detail. So is here. So now so and my students so now so and show this result. So details in the posters and please so discuss on the poster. Okay. Okay, so in final, so this is the final slide. So and the left side. So and by using the optical microscope system, so our microscope system, so and the case of the QBO, so and we can update the sensitivity. So and the such region, so than the current best limit. The current best limit in here. So that's by using the cutting edge technology. So and the sensitivity so will be improved the two or more the higher sensitivity. So it's very I think so it's very interesting. So and now and we are doing that. Okay, so I skip the conclusion. So thank you very much.